Okay, this is exercise 10.3, the discriminant. Now, these notes are from Angela, and she's just sent them to me, and I'm just going to talk through the notes because our screen recorder wasn't working for this lesson. So the discriminant is the, if you look at the quadratic formula, x equals negative b plus or minus the square root of b squared minus 4ac over 2a, the discriminant is the part of the quadratic formula that is underneath the square root sign. In other words, it's the b squared minus 4ac part of the quadratic formula. Now, what's important about this discriminant is that if we work out the value of the discriminant, it will tell us how many roots or solutions there are to a quadratic equation. So the values of x, so for example, if I give you this quadratic, if you look at this quadratic parabola here, sorry, this is a parabola here. This ax squared plus bx plus c equals 0 is an equation, okay? Now, to solve that equation, if you solve that for x by factorizing and you work out what x is, you get the x-intercepts of the equation. Now, these x-intercepts, or the values of x that satisfy this equation, are called the roots of the equation. So if you see a statement saying what are the roots of the equation, or a question saying what are the roots of the equation, it's the values of x. Like if you solve this equation, it's the values of x that solve that equation, or it's actually just the x-intercepts of the graph. So here I've got two roots here, which are the x-intercepts, and here for this concave down parabola I have two roots. So the values of x that satisfy a quadratic equation are called the roots of the equation. And the roots of that quadratic equation there, ax squared plus bx plus c equals 0, are the x-intercepts of the graph y equals ax squared plus bx plus c. Now we're going to look at three scenarios here. In this first scenario, our parabola cuts the graph in two places. So if y equals ax squared plus bx plus c, which is just the general form of a parabola, has two x-intercepts, then the quadratic equation has that equation there, ax squared plus bx plus c equals 0, has two real roots, and we can see 1, 2 roots there, and 1, 2 roots there. This is a concave up parabola where the coefficient of the x squared, which is a, will be positive, and this is a concave down parabola where the coefficient of the x squared, which is the a, is negative. Now, just a new term here, you've never seen this term before, but because this graph, now if we look at this parabola, from here upwards, all the values of y are positive, so there are positive values of y here, and from here downwards, the values of y here are negative. So I might say, right, this is the point 2, negative 3. So this is the point 2.5, negative 1.5, for example. So all the values of y here are negative. Up here on this parabola, all the y values are positive. So anywhere above the x-axis, all the values of y are positive, and anywhere below the x-axis, all the values of y are negative. Now, this is actually called an indefinite function because this function is sometimes positive and it's sometimes negative. Sometimes positive, sometimes negative. So since the graph can be both positive and negative, now what we mean by saying it's positive and negative is that the y values are both positive and negative. It's called an indefinite function. Now you'll remember this a bit better when I show you definite functions, okay? So this is indefinite because it's both positive and negative. Now, the second type of graph here is where the parabola cuts the x-axis at only one point. Now, an example of this graph might be y equals x minus 1 all squared. So y equals bracket, open bracket, x minus 1 squared, which means it's the y equals x squared graph, which would be there shifted across 1 unit to the right. So this graph only cuts the x-axis at one point. So we say, well, this graph, y equals ax squared plus bx plus c equals 0, has what we call one x-intercept, which is just there. If it just has one x-intercept, and so does this one here, then we say the quadratic equation ax squared plus bx plus c equals 0 has one real root. So this is the concave up graph, and looking at the coefficient of the x squared, it's positive, and here is my concave down graph, and the coefficient a of the x squared, so this a value here, is negative, so it's concave down. So here we can see one real root. If we look back up at the graph we were just looking at up there in case 1, we've got 2 real roots, so it cuts the x-axis in 2 places. Real roots means that there is a root that exists. In scenario number 3, we're going to look at not real roots, and you'll understand what I mean. Okay? Now, scenario number 3. If your parabola, or the quadratic equation here, actually just get rid of this equals 0 here, okay? So if y equals ax squared plus bx plus c, get rid of the 0 here, has no x-intercepts, then the quadratic equation ax squared plus bx plus c equals 0 has no real roots. So for example, you might look at a quadratic equation and you won't be able to factorize it at all. And if that happens, then it has no real roots. So see here that the parabola actually sits above the x-axis. So there are no values where this parabola equals 0. Notice here that the y value has been replaced with a 0. And nowhere along here will I get when x is, say, 1, or when x is any value, will y ever be 0. So there are no solutions to ax squared plus bx plus c equals 0. Therefore, we say it's got no real roots. Okay? The reason we're saying no real roots is because when you do extension 2, and some of you may next year, that we look at what's called imaginary roots, okay? So here we can see that the parabola is concave up, therefore a is greater than 0, and that the parabola does not cut the x-axis, so there are no real roots. Now, because this parabola always has positive y values, then it's called a positive definite function. I just say, look at that parabola. It's definitely always positive, but you don't write that. You say, instead of saying it's definitely positive, you say it's a positive definite function. Okay, looking at this parabola, it's concave down. It never cuts through the x-axis. There will be no solutions to the equation ax squared plus bx plus c equals 0. Therefore, we say it's got no real roots. Now look at the values of y down here. They're always negative, the y values here. So we say, well, that parabola is definitely negative all the time, but that's not the terminology we use. We use the word negative definite. So since the graph is always negative, it's called a negative definite function. And just remembering that when we say no real roots, we mean a root is the solution to that equation. So in other words, if I say that's got no real roots there, it means that that equation there has no solution. And if it has no solution, then the parabola will not cut the x-axis. We're doing an investigation here where we're looking at the shape of 4 parabolas. Not the shape of them, actually. We're going to be looking at the discriminant, the value of the discriminant. Remember, the discriminant has special symbol like this triangle, and it's equal to the bit underneath the square root sign here in the quadratic formula, so it's b squared minus 4ac. Now, let's look at this equation here, x squared minus 3x plus 2 equals 0. I know that you could factorize this and work out what the roots are, like where the x-intercepts are, but I want to look at the discriminant only. So here we've got x equals negative b plus or minus the square root of b squared minus 4ac over 2a. Substituting, we get negative 3, which is positive 3, plus or minus negative 3 squared is 9, minus 4 times 1 times 2 over 2 times 1. And then we get 3 plus or minus the square root of 9 minus 8 over 2, which is 3 plus or minus 1 over 2. Now, notice that 1 is a squared number. So the discriminant, which is the bit underneath the square root sign, which is b squared minus 4ac, happens to be 1, which happens to be 1 squared. So if what you've got under the square root sign is a squared number, then when you square root it, you end up with a whole number. And then you end up with really nice values for the roots. See, here we've got 2 solutions. 3 plus 1 over 2, which is 4 over 2, which is 2. Or, sorry, I'll just fix that up. Or 3 minus 1 over 2, which is 2 over 2, which is 1. Now, I could have just factorized this, and I could have said, well, that equals x minus 2 bracket x minus 1 bracket. And when you solve that, you get x is 2 and 1. So if what you've got underneath the square root sign here is a squared number as such as 1, and then when you square root 1, you get 1, you'll end up with nice whole number values here, or you'll get rational values. Like for example here, I could have 3 plus 2 over 5, which is 5 on 2, which is not a whole number, but it's a rational number because it can be written as a fraction. So notice here we've got 2 roots here. Notice that the discriminant equals 1, which was greater than 0. So if the discriminant is greater than 0, you will end up with 2 roots. The reason is you'll have an answer here and you'll get 3 plus something over 2, 3 minus something over 2. So you'll get 2 answers if your discriminant, or what's under the square root sign, is positive. Okay? Now, if what's under the square root sign, which is the discriminant, is also a square number, when you square root that square number, you get a whole number. So you'll also get that your roots are rational numbers. In other words, they can be written as a fraction where b does not equal 0. So looking at this first case, we've got the discriminant is positive, so therefore we've got 2 roots. And in this case, our discriminant was able to be square rooted because it was a square number, therefore our roots are rational. We'll look at the second example now. Okay, this is our second example, and it's x squared plus 4x minus 7 equals 0. So if I look at the roots of this equation, I mean, I cannot factorize that. Be careful, girls, that's a minus 7 here. I cannot find factors, so I'll just move this up a bit. Now, I cannot find factors of negative 7 that add up to positive 4. It doesn't mean that there are no solutions to this quadratic. It means that that I should try and use the quadratic formula to see if I've got a solution or not. So, using the quadratic formula, which is x equals negative b plus or minus the square root of b squared minus 4ac. Sorry, what's wrong with me? It's negative b plus or minus the square root of b squared minus 4ac over 2a. Actually, I was correct. We get x equals negative 4 plus or minus the square root of 4. Sorry, the square root of 4 squared is 16 minus 4 times the a is 1 and the c is negative 7 over 2 times 1. Then we get negative 4 plus or minus the square root of 16 plus 28 over 2, which is negative 4 plus or minus the square root of 44 over 2, remembering that the square root of 44 can be written as the square root of 4 times the square root of 11, and the square root of 4 is 2. So we get negative 4 plus or minus 2 root 11 over 2. Now what I want to do here is divide each of the terms by 2. So that's negative 4 over 2 is negative 2 plus or minus 2 root 11 over 2 is root 11. So we get negative 2 plus root 11. Now there are 2 solutions here. The first solution is negative 2 plus root 11. And the second solution is negative 2 minus root 11. Now you can do those on your calculator, and if you do negative 2 plus root 11, you get 1.3. And if you do negative 2 minus root 11, you get minus 5.3. Now we should write x approximately equals those. So here is our one root here at negative 5.3, and here's the other root here at 1.3. Obviously this parabola is not drawn very nicely. If we look up here at the parabola as well, it's got a y-intercept of negative 7, so you could put negative 7 there. Here we could write negative 5 plus root 11, and over here we, sorry, wrong way around. Here we could write negative, sorry, it's negative 2, I can't even read it properly. Negative 2 minus root 11, and at this point here, at this x-intercept, we can write negative 2 plus root 11, and here on the y-intercept we can write negative 7. So girls, here we do have 2 roots here, but the thing is, because the b squared minus 4ac bit, which is the 44 answer that we got here, is not a square number, then you can't square root 44, and so your roots are what we call irrational, IRR, so it's irrational, and those roots, if you can please write them on the graph, they are negative 2 plus root 11, so just write that here, and this root, just put a dot there, it's negative 2 minus root 11. So those roots are not rational, but there are still 2 roots. So if the discriminant is positive, you always get 2 roots. But because our discriminant is not a squared number, then the roots are irrational or not rational. Now we'll do example 3. It's our third example, and it's x squared plus x plus 5. Now if you try and factorize that, looking for factors of positive 5 that add up to positive 1. You're not going to find any. But we still need to check with the quadratic formula if we have roots to this equation or not. So doing x equals, using the quadratic formula, x equals negative b plus or minus the square root of b squared minus 4ac. Looks like we've got a little mistake here. So you're going to have to fix that up. We've got x equals negative 1. So please put a negative in front of there. Plus or minus the square root of 1 squared is 1 minus 4 times 1 times 5. And we get, please put a negative here as well. You get negative 1 plus or minus the square root of 1 minus 20 over 2 times 1, which is 2, which is negative 1. I think this is the negative down here because I can see this equal sign with 3 bits in it. Okay, so it's negative 1 plus or minus the square root of negative 19 over 2. Now that cannot, there's no solution to this because the discriminant, the bit under the square root sign, is negative, so there's no solution to this. So here we notice that the discriminant is negative. In other words, the b squared minus 4ac bit is less than 0. So therefore, this equation will have no real roots. But we know that the y-intercept of this equation is 5. But to draw it, so it's going to look like that. To draw it a little bit more accurately, you could find out where the axis of symmetry is. I'm just going to quickly do that. So just listen to what I'm saying. It's x equals negative b over 2a. So the discriminant would be negative 1 over 2 times 1. It's negative a half, not the discriminant. The axis of symmetry is x equals negative a half, which would be about there. You should then find the minimum value of the parabola as well. Okay? Just give me a minute. I'll just try and fix this up. You could find the minimum value of the parabola by substituting x is negative a half. I'll just quickly do that here. Negative a half squared is a quarter. A quarter minus a half is negative a quarter plus 5 is 4 4/4. So this point, the vertex, it's not drawn very well here, but it's negative a half, 4 4/4. But look, the y-intercept here is 5. It definitely has no real roots. And the reason it's got no real roots is because the discriminant is negative. So if the discriminant is less than 0, then there are no real roots. We're going to look now at the fourth case. Fourth example, x squared minus 6x plus 9 equals 0. If we look at the discriminant here, negative b plus or minus the square root of b squared minus 4ac over 2a, we get negative 6, which is positive 6, plus or minus the square root of b squared is 36 minus 4 times 1 times 9 over 2 times 1. And we get 6 plus or minus 36 minus 36, which is 0. Now, because we've got nothing here, it becomes 6 plus nothing over 2, or 6 plus or minus nothing over 2. Remember, the square root of 0 is 0. So it just becomes one solution, 6 over 2, which is 3. So if the discriminant, which is the b squared minus 4ac bit, is 0, then you don't have two solutions, you only have one, because it's 6 plus or minus nothing over 2, so it's just 6 over 2. So if the discriminant is 0, therefore you get one root, and we write one real root. Now, if I try and sketch this parabola, I know here that the y-intercept is 9, because if I put when x is 0, y is 9. Also, I can find the axis of symmetry. Remember, it's negative b over 2a, so it's negative 6, which is positive 6 over 2 times 1. So it's 6 over 2, which is 3. In other words, this parabola has an axis of symmetry of x equals 3, which is this line down here, and it's got a y-intercept of 9, so therefore it looks like that. Now, the other way I could sketch this, the only reason I'm doing this is so that you can see the value of the discriminant. I know that you could easily sketch this by factorizing it because it's a perfect square and you get x minus 3 all squared in brackets equals 0. So x minus 3 in brackets squared equals 0. So therefore x is 3. So this is really just the parabola y equals x squared shifted 3 units to the right. But the thing is the discriminant 0, therefore the parabola has only one root, which means it only touches the x-axis at one point. And, for example, the vertex of this equation would be 3, 0. If I substitute x equals 3 in here, I get 9 minus 18 plus 9, which is 0. So the vertex here is 3, 0. Again, parabola only having one root, only touching the x-axis at one point. Summarize all of these findings from the 4 examples. So summary of discriminant, which is the triangle symbol, which equals b squared minus 4ac. Notice that if the discriminant is positive, that there are 2 roots. Now this is point number 1, but I've got point 1 part A and point 1 part B. Again, if the discriminant is positive, so if b squared minus 4ac is positive and the discriminant is also a square number, for example 1, 4, 9, 16, 25, 36, etc., then yes, there are still 2 real roots, but they are rational roots. In other words, they can be written as a fraction. Rational means a over b, where b does not equal 0. So you've got 2 real rational roots if the discriminant's greater than 0 and the discriminant's also a square number. But if the discriminant's greater than 0 but not a square number, for example, if the discriminant might be 19, so you get square root of 19, then you're going to get 2 roots, but they're not going to be rational. Okay? Now, the diagrams that go with 1 are here. I can have the concave up parabola with 2 roots, or I'll just try and move that, or I can have the concave down parabola, which has 2 roots. Okay, so in this case, discriminant is greater than 0. Here, discriminant's also greater than 0. But here, the a is greater than 0. The coefficient of the x squared is greater than 0. Here, the coefficient of the x squared, a, is less than 0 because it's concave down. Now, we also notice scenario 2 that if the discriminant, b squared minus 4ac, equals 0, then we have what we call 1 real root or 2 equal roots. I know this sounds funny, but the reason it's called 2 equal roots is you might have something like this, concave up here, and this might be y equals, the equation of this might be y equals, open bracket, x minus 1, close bracket, squared. So you've got x minus 1 squared equals 0. Well, that really is x minus 1, bracket, again, x minus 1 in brackets equals 0. So your roots are x equals 1 and 1. So you've got 2 roots, but they just happen to be the same. The reason there are 2 roots is that because it's a quadratic equation and it's got power of x squared, it has to have at most 2 roots. But in this case, the roots here are equal. So this is the concave up version, where the a is greater than 0, but discriminant equals 0. So you've got 1 root here, and this is the concave down type graph where you can have 1 real root as well. So in this one, here you can write a is less than 0, meaning that it's concave down, but discriminant, triangle symbol, equals 0. Okay? Now you might want to put this drawing underneath point 2, and these drawings up here underneath point 1. Okay? Now, for point number 3, we've noticed that discriminant can also be less than 0. And if the discriminant's less than 0, then there are no real roots. When we say no real roots, we mean that the roots are imaginary. The reason we call it imaginary is that you cover that. Some of you will be doing that when you do Extension 2 Maths next year. So the roots are not real. Now, that will happen if, I'll just minimize this a bit. That will happen to draw the 2 scenarios for situation number 3 where the discriminant is less than 0. We have you've got this parabola up here where it does not cut the x-axis at all. So here, can you please write that a is greater than 0 because it's concave up. So the coefficient of the x squared term is positive, but here discriminant, the triangle symbol, is less than 0. And here, sorry, I just got to move this. Here's your other version of discriminant less than 0, but here a is less than 0 as well because it's concave down, and discriminant, which is the triangle symbol, or you can write b squared minus 4ac, is also less than 0. Notice in scenario number 3, we've got no real roots. The parabola does not cut the x-axis at all. Okay, so that's a summary of the discriminant. Some examples of using this information that we've just discovered about the discriminant. So if we just look at the discriminant only and look at the equation of the parabola or the quadratic equation, you can tell by looking at the quadratic equation whether the parabola is concave up or not. And by just looking at the discriminant, you can see how many roots the equation has. Okay? Now, in this first question, it says find the discriminant, and there should be an and here, and describe the roots of the following quadratic equations. So the first example is from exercise 10.3, question 2a, and the equation is x squared minus x minus 4 equals 0. Now, please don't do all this x equals 1 and this 2. Can you just rub that all out and the plus or minus and just put discriminant equals? So actually just do it over here. So discriminant equals, b squared minus 4ac, which equals negative 1 squared, which is 1 minus 4 times, so just do this bit, just write this bit. So it's negative 1 squared is 1 minus 4 times 1 times negative 4, and you'll get that the discriminant is equal to 17. You don't actually have to do the whole quadratic formula, so I just want you doing the discriminant. I think it's actually done correctly in example 2 below. So you just want the triangle symbol equals b squared minus 4ac, then work it out, you'll get 17, and then you'll make this conclusion that b squared minus 4ac equals 17, which is greater than 0, therefore discriminant's greater than 0, therefore there are two real irrational roots because this discriminant is not a squared number such as 9 or 16 or 25. Okay, we'll look at example 2 now. Okay, I'll just put up example 2 here. So example 2 is, I might just put up 2 and 3. I'll just fix it up. All right, example 2 is 2x squared minus 3x plus 6 equals 0. So we get, actually this graph's not very good. So we get discriminant is b squared minus 4ac, which is 3 squared minus 4 times 2 times 6. Because here a is 2, b is 3, c is 6. And we get that the discriminant is 9 minus 48, which is negative 39. So therefore, the discriminant's less than 0. So therefore, this equation has no real roots. Just be careful here. I'd probably draw that a little bit higher. I know we've drawn it here, but let's just see what the axis of symmetry is. And it's negative b over 2a. So the axis of symmetry is negative 3/4. So the axis of symmetry is about there. And I'd say the graph, just make sure it's not touching the x-axis here, please. So just draw it a bit higher and the axis of symmetry a little bit closer to the y-axis. Okay, so there are no real roots with that one. Now, question 2c. Here's the next question. X squared minus 9x plus 20 equals 0. Looking at the discriminant here, we get discriminant's b squared minus 4ac, which is negative 9 squared, which is 81, minus 4 times 1 times 20, which is 81 minus 80, which is 1. Now 1 is a square number because 1 squared equals 1. So again, the discriminant's positive and the discriminant's a square number, therefore you'll have two real rational roots. Now if I actually work out and factorize this and work out what the roots are, if I factorize this, I get x minus 5 so open bracket x minus 5 close bracket, open bracket x minus 4 close bracket equals 0, and my roots are 4 and 5. Okay, and it's concave up because the coefficient of the x squared is 1 and it's positive, and the y-intercept's 20. So doing a quick sketch here, we can see that our roots are 4 and 5, and yes, they are rational. But by just looking at the discriminant, you can tell that the roots will be rational. And by looking at the equation of the quadratic, equation, you know that this is concave up because of the a value, which is 1. Now, this is one of my examples. Okay, this example is x squared plus 8x plus 16 equals 0. Again, this is concave up. The y-intercept is 16, but if we look at the discriminant, which is b squared minus 4ac, we get b squared is 8 squared is 64 minus 4 times 1 times 16. So we get 64 minus 64, which is 0. So therefore, this means that this equation has only one solution or one real root. Now, if I factorize that, x squared plus 8x plus 16, it's a perfect square. And when I factorize it, I get x plus 4, close bracket, squared equals 0. Therefore, x equals negative 4. So this really is the x squared graph shifted across to the left 4 units, and it looks like that. Notice there's only one real root, and therefore the discriminant will equal 0. We're now going to do some more examples from the exercise.